What is up, Flutter devs? Today we're going to create Conway's Game of Life using the Flutter processing package. Let's go figure it out. So first, what is Conway's Game of Life? Well, I don't really remember. This was a topic back from the early part of my computer science program, but it is an instance of cellular automata, or what is called here cellular automation. In a very generic sense, we have a grid of cells. Those cells, every cell is considered either alive or dead. If it's alive, you see here it's colored in black. If it's dead, it's in white. Every iteration, every kind of game frame, you decide which of those cells continue to live or die or are born. And then based on a very basic set of rules, you can get very interesting emergent behavior. Now, there's also, when you get more into the computer science part, you see things like this. It is Turing complete and can simulate a universal constructor or any other Turing machine. That gets much more into the science of computation, not something we're focused on here today. This is an exercise for Flutter processing. And in fact, I should point out that this is coding challenge number 85 over on the coding train, which is why we're doing it here. From a processing perspective, a UI perspective, our goal is to paint this thing that you see over here on the right. Now, we're not going to create exactly this because this is a very carefully designed kind of iteration of Conway's Game of Life. These cells were chosen specifically to get this effect. We're going to choose random cells, but we're going to implement the painting of this, and we're going to implement the standard rules for Conway's Game of Life, which are right here. Technically, these 4 rules, but they can be reduced to these 3 here. So for example, any live cell with 2 or 3 live neighbors survives. So if you are a black cell and you have 2 or 3 black cells around you, you survive. If you're a dead cell, meaning you're white, but you have 3 black square cell neighbors around you, you are born into a black cell, a live cell on the next iteration. All other live cells die. So if you're a live cell with 0 or 1 live neighbors, if you're a live cell with 4+ live neighbors, you die. And I guess, of course, if you're already a dead cell, then you're a dead cell. But we're going to implement these rules, which will give us this emergent behavior that you see up here. So how are we going to do that? Well, I already have the example app running. So this is a sketch waiting for us right here to fill in. Let's go implement what we can. In terms of thinking about how we're going to approach this, again, notice that we're on a grid. So we have this essentially a glorified 2-dimensional array filled with booleans, true for alive, false for dead. We just need to set that up, give it a random set of values, and then paint it, and then we implement the rules for the next generation. Let's go figure that out. Here's our sketch. Let's start by configuring the size of our canvas. So we'll say size is 500 by 500. Doesn't matter what size you choose. It's just a matter of preference. And then because we're drawing a grid, we need to decide how many pixels per grid square. Now, what you could do is you could take all of the available space and then divide it by your desired row count and column count. That's one way to do it. Another way to do it is to say, I want X number of pixels per cell, and then you have as many rows and columns as you can fit. And we're going to take that latter approach, again, primarily for preference. So we'll say pixels per cell equals 25. And because we're establishing the number of pixels per cell, it means we have a possibly, essentially a variable column count and row count based on dividing the width and the height by that value. So we're eventually going to have a number of columns, and we're going to have a number of rows. And then I said we need a grid full of booleans. How do we get that? Well, in our case, we're going to have a list of booleans, which is functionally the same thing as like a 2-dimensional array. A list of lists is a 2-dimensional array. This is what we're going to need to set this up, paint it, and generate future grids. Grid refers to the cells. It's the current generation of cells. Now down here in setup, we just decided what the width and height would be, which means we can now calculate the column count, which is the width that we just chose divided by pixels per cell, and we're going to floor that. Row count is height divided by pixels per cell. I'm assuming square cells here. We'll floor that. Okay. And then we need to actually generate our first generation of cells. So we're going to say grid is equal to list dot generate, and we're going to generate each column, and then each column is going to be a list dot generate, where we generate each individual cell. So we're going, in that case, we'll need, the first generation is the columns, the second generation is each row within the column. And then we're going to use a random, which I think we can say const random. And once again, this autocomplete is taking forever, probably because of the recording. I guess something's changed in my recording software that has made it slower. So we will say next Boolean. So we can actually generate a random Boolean. And let's see, let me get the const working here. Nope, still doesn't like that. Okay. So in some languages, you can only generate doubles, random doubles, and then you have to convert that into integers or booleans or whatever. We can just ask Dart to give us a random Boolean. And let me try to get some auto formatting going here. Okay, so there's our grid. Now come back over here, you'll see that we are now 500 by 500, but we aren't drawing the grid. We've generated a grid, we haven't drawn anything yet, so we need to figure that out. But we're on our way. Okay, now down here in the draw method, this is where we actually start painting things. First, we're going to set the background to black. So whether you choose black as alive or dead in terms of the cells is your choice. We're actually going to have black be dead, and so then only little white cells pop up, which is kind of the inversion of what we saw in the Wikipedia article. Now, once we've filled the screen with black, we're going to draw whatever cells or grid items are active. For that, we're going to set the fill color to white, and then we're going to say for column from 0 to column count, increment by 1. So we're going column to column to column, and then we're going to go from row is 0, row is less than row count, row plus equals 1. And then now we're dealing with an individual cell, so we need to paint it. First, let's calculate the top left of that cell. It's going to be equal to, the x value is going to be the column times pixels per cell. And the row, or the y value, is going to be row plus pixels per cell. That's the top left of this particular cell. And then we're going to say, actually, we only need to paint if grid column row is true, so only if we're alive. Then we're going to paint something. And we're going to say rect from left top with height. So top left dot dx, top left dot dy, pixels per cell, and pixels per cell. This should now draw a square at this given top left, which is white, only for the cells that are alive. Let's save that. Might need to do, let me real quick do a hot restart. I want to make sure that I got this value up here. Okay, so definitely done something wrong here. Let's see what I screwed up. Column 0, yeah, okay. And let's turn off the drawing here. What was that method called? Oh, it's no loop. That's what I'm thinking of. No loop. Okay. Let me clear this out. Let me restart that. Okay, so we're always drawing at the same y value. Or similar y value. Well, did I not? Oh, okay. Need to multiply by pixels per cell. And now we have a grid. And this is probably a high density for Conway's Game of Life, but nonetheless, there's a grid. Okay. So now if we take that grid and we apply the rules to it, then we will get this animated Conway's Game of Life. Therefore, down here, after we draw everything, we're going to call a method called create next generation. And this is where we're going to apply the rules. Void create next generation. So we're going to need a new grid because we maybe there's a way to apply this in place, but I doubt it. Because we need to calculate based on our neighbors, if we change the grid in place, then by the time we get to the next cell, we've screwed up the neighbors because we applied changes to the previous cell. So we need a new grid, which we will fill based on the previous grid. And once again, we're going to start by generating the cells, except we're going to start them all as false because we're going to fill this with what we want. So now we're going to loop. I'm going to copy this loop because we're going to go through all the cells. We're just going to do something different. We're not going to draw. We're going to calculate based on the rules. And then rather than in the middle of this loop, add the rules, what we're going to say is new grid. And let's see, how did I index this before? Column, then row. So column, row equals calculate next cell value, and we're going to pass a column and a row. We're going to defer the exact application of the rules to this method. And then once we've calculated the new generation or the new grid, we're going to say grid equals new grid, and that'll be picked up on the next frame. Now we're going to define this calculate next cell value, which takes in required int column, required int row, and we need to return whether or not this cell is alive or dead. This is where we actually bring in those rules that we saw. Now these rules pretty much all come down to one number, which is given this cell, how many live neighbors does it have? Based on the number of live neighbors, we decide whether this cell continues to live or dies or is born. So we're going to say live neighbors count equals 0. And then we're going to go through and manually find all the live neighbors. Now you can try to do some kind of neat math on the index to figure out the neighbors. We're just going to go manually look for everyone. So we're going to look for the top left, the top right, the bottom right, the bottom left, and then we're back up to the top left. Okay, so live neighbors count plus equals. So one thing that we need to keep in mind here is that if we look to the left, for example, if we're at column 0, there is nothing to the left. And all of these directions are going to have that possibility. So we need to make sure that we're within the board before we go accessing the grid. So we're going to say if column is greater than 0, and then we're going to actually access the grid, and we're going to say column -1, row -1. And I forgot one more condition here. So if we're going top left, we need to make sure that not only is column greater than 0, but row is also greater than 0. What we're saying here is if we are at least somewhere to the left of the grid, so we're somewhere beyond this leftmost column, and we're somewhere beyond this topmost row, then we go to the top left. We go up 1 and over 1, and we see if it's alive or dead. If it's alive, we add 1 to the live neighbors count. Otherwise, we add 0, and live neighbors count doesn't change. This is essentially what we need to repeat for each of these neighbors, and then we'll be able to evaluate the rule. Up top, we're going to say live neighbors count plus equals. What do we need to check here? If we're going up, we need to make sure the row is greater than 0. And then we can access the grid, and we can say column and row minus 1, add 1 or add 0. For the top right, live neighbors count plus equals. We're going to make sure that column is less than column count minus 1 and that row is greater than 0. And then we're going to access the grid at column plus 1, row minus 1. So we're going over to the right 1, we're going up 1 on the Y. Fix a typo there. Live neighbors count. We're going 1 to the right, which means that column needs to be less than column count minus 1. We're not going up or down, so we don't care about the row. We just need to check the grid. Column plus 1, same row, plus 1 plus 0. Live neighbors count. So now we're going to the bottom right. We need to make sure column is less than column count minus 1 and that row is less than row count minus 1. And then we're going to access the grid at column plus 1 and row plus 1. Add 1, add 0. Bottom, live neighbors count plus equals. Now we're going down a row, but we're not going left or right, so we don't care about the column. We need to make sure that row is less than row count minus 1, and then we check the grid at column and row plus 1, add 1 or 0. Live neighbors count. We're going 1 to the left and 1 down, so column needs to be greater than 0, and the row needs to be less than row count minus 1. And then we check the grid at column minus 1, row plus 1. Then we plus 1 or plus 0. And then finally to the left, live neighbors count plus equals. We're going column to the left, but no change to the row. So column needs to be greater than 0, but that's all we care about. So we say grid column minus 1, same row, plus 1, plus 0. Okay, all of that annoying manual stuff aside, we now have the live neighbors count, and now we can apply the rules. So what did the rules say? So if the current cell is already alive, so if grid column row and live neighbors count is greater than or equal to 2, and live neighbors count is less than or equal to 3, so 2 or 3, then we stay alive. We return true. We'll say the living cell survives. Else, if this cell is dead, so if not grid column row, if it's currently dead, but live neighbors count is equal to 3 exactly, then we say a dead cell is born and we return true. And then in all other situations, the cell dies or remains dead. We return false. Okay, and then I'll need to fix a typo there. Calculate next cell value. So I think that's everything we need. Let's save it and see what happens here. All right, check that out real fast. I guess that's a steady state. I don't know. Either that or maybe our logic is wrong. But one thing is for sure, this goes way too fast. We don't want to watch this thing go this fast. Anytime that you want to slow down the drawing in Flutter processing, you can just come in here to setup and you can say frame rate, in this case, equals 3. And now you can see it much more slowly. You can make that a little higher if you want, but 3 times a second, we're calculating a tick or a game frame or a game loop, however you want to look at it. And then down here, I can't remember when I added this. Maybe it was here in the previous video, maybe it wasn't, but we can restart sketches with this little button, which is nice when you have something that actually changes state like this. We just keep restarting. But with that, we have Conway's Game of Life. And this, again, is coding challenge number 85. So you can go over to the coding train and see how Dan did this same thing. But we will continue with some more coding challenges, replicating what Dan has done over on the coding train until we've stress tested the Flutter processing package a bit. And then we'll eventually consider this whole exercise to be complete. So I hope you enjoyed that. Maybe you learned something about cellular automata or automata, depending on how you want to pronounce it. And I'll see you in the next video.